What's up, guys? It's me, Sir Ernest, and today we're going to talk about mechanics of rigid bodies. So, for example, if we have, let's say, we have a rod, and this rod is rotating about its center. If this is a uniform rod, doesn't matter, no? But for example, if we have four particles, uh, this particle, this particle, this particle, and this particle. And let's say this particle starts to rotate by, let's say, 90 degrees. So after some time, this object will now be oriented this way. Okay, so if this object is a rigid body, that means these four particles, so let's call this particle 1, after rotation, it will be located here. This particle will be located somewhere, say somewhere here. This particle will be located here, and this particle will be located here. Now, in order for this object to be rigid body, that means the relative distances between these particles is the same as when it is in its original position. Okay, so that's your rigid body. Now, we already discussed center of mass before, right? But that during that time we only discuss the center of mass of system of particles or discrete number of particles. So let's say we have a system that has, let's say, uh, 1, 2, 3, 4, 5, 6 particles. So in three dimension, this the system of particles have its center of mass defined by the its x component xcm, y component ycm, and z component zcm. So for a system of particles like this, the x component, if you could recall, is just equal to the sum of the product of the masses of each of the particles mi, where I is a representative particle here, and its product with the x component of the position of, for example, this particle. And then you divide it with the total mass of the system. So this is the x component of the center of mass. The y component and the z component of the center of mass will follow the same form, wherein the y component will be equal to the sum of xi. This should be yi for all I divided by sum of mi for all I. And lastly, the z component will be the same form. This is the sum for all I of zi mi divided by sum of mi. Okay, so these three components xm, y, cm, and zcm is the center of mass, will define the center of mass of the system of particles. Now, for a rigid body, what we have will be this. Okay, so we can group them as follows. We can group them as a continuous mass distribution, a thin shell of negligible thickness, and a thin wire of negligible thickness as well as negligible width. So for a continuous mass distribution, what we have would be a volume integral. So the x component will now be in the form of sum of rho times x dv, where rho dv is your differential mass. So that's the mass of one element. So later on when we have examples, this will make more sense. Anyway, so this becomes a volume integral divided by the total mass, which is equal to the integral of rho dv for all v. Same form will you will have the same form for y component. So this is integral for all v for the whole volume of rho y dv, then divided by rho dv for all v. And then ccm will follow the same form. Okay, so here we assume first that the density rho is not uniform. So it's not automatic that your density rho, this is your volume mass density, is is can be factored out of the integral sign. Now, if we have a thin shell, so this becomes a two-dimensional problem. Earlier, we have a three-dimensional problem. So in this case, instead of a volume element, what we now have is a surface element. So the x component will now be in terms of a surface integral. So the surface integral of rho x ds, where ds is your volume surface element, rho is your surface mass density. Here we define that the element dm is equal to rho ds. Okay, then we divide this by rho ds for the whole surface. And then we use the same form for ycm and zcm. So this is integral of rho y ds for all s, integral of rho ds for all s. And then this becomes zcm would be integral of rho z ds for all s, and then divided by the total mass, which is integral of dm, which is integral of rho ds for all s. Now for a continuous mass distribution, you have a three-dimensional problem. For a thin shell problem, we have a two-dimensional problem. So therefore, a thin wire problem will only require us to have a one-dimensional problem, which translates to a line integral. So you can now write the following. XEM becomes a line integral. So this is rho x dl. Here we define dm to be rho dl. Rho is your linear mass density. So this integral will be a line integral. So the total mass would be the integral of dm. So this is rho dl for the whole length. Then ycm would follow the same form. So this is integral of rho y dl for all l, integral of rho dl for all L. ZCM would be equal to rho Z dl for all L. Then with this becomes over integral of rho dl for all L. Okay, so this is now your center of mass for x, or this is now the the x, y, and z components of the center of mass for these three different configurations: a general continuous mass distribution, a thin shell, and a thin wire. So in the next video, we're going to have several examples on how we use these equations. So for now, thank you guys for watching. I hope you learned something today, and I'll see you guys in the next video. Bye-bye.